So continuing with optimization problems, in this video we're going to solve the following problem. Let's say we're given a cylinder. So let's say we're given a cylinder that has the following dimensions. It has radius r and it has height h. Now the problem is the following. We want to fabricate a can that has this cylindrical shape, but we want it to hold a volume of exactly 50 centimeters cubed. So that's the volume that we need to make sure it contains. The problem is that we want to minimize the amount of material that we want to use on the actual construction of this can. So we want to minimize the amount of material. So that means the amount of surface area that we use on it. So we're going to ignore the thickness of the walls on the top and the bottom. We're only going to focus on the surface area of the can. So we want to minimize the surface area. So we have to work out, first of all, what is the function of surface area with respect to those two variables? And what is the constraint going to be? Well, first of all, we gotta find what the surface area function is going to be. So the easiest way we can do that is, let's try and open this up. So let's open this up and imagine that we have something like this. So if we join the two sides, we create the cylinder. So the total length of this sort of rectangle that we have here, if we stretch it out into a rectangle, that's going to be the length of one of the sides. This is just going to be the circumference of that circle. So the circumference is going to be 2 pi r. And now what is going to be the height of the rectangle? What the height is just going to be h. So for our surface area, we're going to have the surface area of the wall. That's going to be 2 pi r times h. Now that's one of the components. We also have a top and a bottom. And those two areas are just going to be circular areas of the same dimension. So that's going to be 2 times pi r squared, because pi r squared is the area of a circle. So this is going to be the function of surface area for this example. Now what is going to be the volume? Well, the volume is going to be the area of the circle, so that's pi r squared, times the total height, because you can imagine that if you break this into little slices, you can have h number of circles overlapping on top of each other, and that will give you the measure of the volume. So this is going to be pi r squared times h. That's going to be the volume. And this is actually the constraint, because we need the volume to be equal to 50 centimeters cubed. So this is going to be our constraint equation. So just as we did in the last video, what we need to do is we need to express our function, the function that we're optimizing, in terms of a single variable. So in order to do that, we will use the constraint equation to find another expression for one of the variables in terms of the other. In this case, I'm going to make h the subject, and I'm going to express it as 50 over pi r squared. So now I'm going to substitute back into the surface area equation. So this is going to be 2 pi r times 50 pi r squared plus 2 pi r squared. So let's see what we have when we simplify this. Well, surface area is going to become equal. This pi and this pi are going to cancel out. This is going to cancel out with one of the r's, and 2 times 50 is 100. So this is going to be 100 over r squared plus 2 pi r squared. Actually, this should be just r, because one of the powers cancel that with this r. So that's going to be our surface area equation. Now to optimize this, we're going to find the derivative with respect to r. So ds over dr is going to be what? Well, you can express this as 100 r to the minus 1. And you know from the chain rule of differentiation that you can take the minus 1 down. So that's going to become minus 100. And then you have to subtract 1 from the power. So this will become r to the power of minus 2, which is the same as 1 over r squared. And then this is going to be plus 2 times 2, that's 4 pi r. And we want to make this equal to 0 because we want to find these stationary points that will give us maximum and minimum values. So after a little bit of algebraic manipulation and rearrangement, we find that r should be equal to the cube root of 100 over 4 pi, and this should be approximately equal to 1.9965 centimeters. And now using this value, we can find the value of the height. So h is going to be 50 over pi r squared, and this is going to be approximately equal to 3.993 centimeters. Alright, so now that we have those two things in place, we can actually proceed to find the minimum surface area that we can actually build that will contain the volume of 50 centimeters cubed. So I'm just gonna make some room in here. What is going to be the minimum surface area? Well, it is going to be the following. Minimum surface area is going to be equal to, or approximately equal to, 57.13 centimeters squared once we plug all the values so far back into this equation. So this is another important application of calculus to optimization, and you saw that we can actually treat any three-dimensional shape and optimize it in terms of dimensions, but optimization spans a whole wider range of different fields. So it can be used in economics as well to optimize the amount of profit or the amount of or the cost of a particular utility or a commodity and things like that. So it can be used in a wide variety of different situations, not just in geometry and things like manufacturing, but a lot of different very interesting things. So I'm going to leave optimization here now, and in the next video we're going to get started on integral calculus.